Shear force and bending moment are a part of structural mechanics which belongs to the civil engineering field. These two terms are very important for designers because they represent the ways in which a structural member can fail. Before explaining these terms, I would like to highlight many points which are related to the topic and applying them to a beam as a member of building structure. Type of beams according to supports. Simply supported beam. A beam is supported at two ends which are free to rotate and have no moment resistance. The pin is restrained in two reactions and the ruler is restrained in one reaction. Cantilever beam. A beam is fixed at one end and free on the other, which is restrained in two reactions and moment. Overhanging beam. One of its ends is extended beyond the support. Fixed supported beam is supported by fixed at both ends. And continuous beam, a beam having several spans in one straight line, generally has at least 3 supports. Type of loads. Point load. A load acting at a point on a beam as shown in figure 1a. Uniformly distributed load UDL, a load which is spread on a beam as shown in figure 1b. Uniformly varying load, a load which is spread over a beam in varying uniformly manner as shown in figure 1c. Type of beam according to statically determinate and indeterminate. Determinate beam, a beam has 3 or less and none and can be solved using the 3 equilibrium equations. Indeterminate beam, a beam has more than 3 and none and can be solved using stiffness or moment distribution methods and so on. Having understood the introduction, let's define shear force and bending moment with example. Shear force is a force that produces a shear failure at a given point in a beam, and it's clear in a brittle material such as a concrete as shown in figure 2a. Shear force diagram. The diagram shows the variation of shear force along the length of the beam. The bending moment is the magnitude of the bending effect at any point in a beam, and it's clear in a ductile material such as steel as shown in figure 2b. Bending moment diagram. The diagram shows the variation of bending moment along the length of the beam. Note that brittle materials are not giving a warning before a failure as shown in stress strain curve for concrete in figure 2a. Compare it to ductile materials which are given a warning as shown in a stress strain curve in figure 2b. The curve changes from elastic zone to plastic zone through a yield point. Sign convention for shear force and bending moment. Sagging bending moment assumes to be positive. Hugging bending moment assumed to be negative. Moment clockwise assumed to be positive. Moment anti-clockwise assumed to be negative. For shear force, the force direction upwards assumed to be positive. The force direction downwards assumed to be negative. After these highlight points, let's solve this example. Overhanging beam with UDL and point load is supported by pin at A and ruler at B as shown in figure 5. Draw the shear force and bending moment diagram. Sketch the deflected form for the beam. Identify the position of the contra point. To draw shear force and bending moment diagram, we should calculate shear force and bending moment at each point on the beam following the steps. Change support to reactions. Draw a vertical line from each point. Draw baseline for shear force and bending moment diagram. Calculate reaction at the support by using the equilibrium equation. RB equal 35 kilonewton. RA equal 25 kilonewton and Rx equal 0. Calculate shear force at C, taking either the left or the right side of the point C using a summation of Fy equal 0, shear force at C equal 15. Now we can draw shear force diagram, follow the force direction, start from point A, draw an inclined line from A to C, from C to B, nothing. On B, go up to 35. From B to D, nothing. And from D, go down 20 to 0. The shear force diagram shows that there are two contrapoints. Contrapoint when shear force changes from positive to negative or opposite. To draw bending moment diagram, we have to calculate a moment at each point on the beam, taking either the left or right side of that point. Using summation of moment equals 0 assumes moment clockwise is positive and moment anti-clockwise is negative. Note that the maximum moment when the shear force is 0. For this example, we have two maximum moments, one in the positive zone, point E, and one in the negative zone, point F. Determine the distance x from contrapoint to point A in order to calculate the moment at point E. X equal 2.5. Therefore, moment at E equal 31.25 kilonewton meter. Moment at F equal 40 kilonewton meter, and moment at C equal 20 kilonewton meter. Having calculating moment at each point, let's draw the bending moment diagram. Start from point A. Draw parabola curve from point A to C, which represents the UDL. Draw inclined line D to F, and again an inclined line from point F to C. It's shown that we have a contrapoint on bending moment diagram, and the deformed shape of the beam as shown here. There is another example to solve it using the same procedure, but unfortunately the time is limited. Figure 7 shows the deformation of building frame structure. Summary of this lecture, references, and thanks for listening.